So guys, welcome to our channel once again. In today's video, we have here 10 questions to answer on the topic heat energy. So guys, this video will be about latent heat, melting point, and specific heat capacity. So let's go ahead and start with the first question here. It says, calculate the change in volume when 90 grams of ice is completely melted. So take the density of water to be 1 gram per cm cube and density of ice to be 0.9 gram per cm cube. So guys, actually, since we are calculating for the change in volume, that's the delta V. It will be the volume V2 minus V1. So in that case, guys, we are going to calculate for the volume of ice and then the volume of water and then find the difference here, and that will be the change in volume. So let's go ahead here. For the volume of water here, we are going to have that volume is equal to mass over density. Since density is mass over volume, then volume is mass over density. So 90 gram over 1 gram per cm cube will be 90 cm cube. So guys, that will be the volume of water here. Then for the volume of ice, that will be 90 over 0.9, so that would be 100 cm cube. So guys, when we do 100 minus 90, we're going to have 10 cm cube here, and that's option C. So guys, the answer to this question is option C. Let's go ahead and consider the next question, guys. So that's question number 2 here. It says an immersion heater rated 400 watts 220 volts is used to heat a liquid of mass 0.5 kg. If the temperature of the liquid increases uniformly at the rate of 2.5 degrees Celsius per second, calculate the specific heat capacity of the liquid. Assume no heat loss. So guys, for a question like this, if we use the formula IVT is equal to MC theta, we are going to have that since we don't have all the parameters here, I is actually current and V is voltage, then T is the time, then M is the mass, C is the specific heat capacity, and then theta is a change in temperature. So guys, we don't have the current here, but we actually have power. So we can have that IV is equal to P, and then we change that in this equation. So this equation becomes PT is equal to MC theta. So to find C now becomes PT over M times theta. So in that case, the power is 400 watts, then times the time, which is 1 second, then all over the mass of 0.5 kg times the change in temperature 2.5 degrees Celsius. So guys, let's go ahead and calculate this out together, and we're going to have 320 joule per kilogram per Kelvin, and that's option B here. So guys, that's the answer to this question. Let's go ahead and consider the next question, guys. So that's question number 3 here. It says a body of mass M has a specific heat capacity S and a heat capacity C. If the temperature of the body changes by 0 degrees Celsius, which of the following equations is correct? So guys, for this we are going to have that heat loss will be equal to heat gained. So if heat loss is heat gained, so we are going to have C theta is equal to MS theta. So we can cancel out theta in this, and then we have that C is equal to MS, so MS is equal to C. Option C is the answer to this question, guys, and that's MS is equal to C. So that's it for this question. Let's go ahead and consider the next question, guys. So guys, the next question here is question number 4, and it says, calculate the quantity of heat needed to change the temperature of 60 grams of ice at 0 degrees Celsius to 80 degrees Celsius. So guys, here we're given the specific latent heat of fission to be 3.36 times 10 to the power of 5. Then the specific heat capacity of water is 4.2 times 10 to the power of 3. So guys, we're simply going to have that the total heat here will be the heat needed to melt the ice at 0 degrees Celsius from solid to liquid at 0 degrees Celsius. Also, this plus the heat needed to heat the water from the 0 degrees Celsius to 80 degrees Celsius. So guys, here we're going to have the total heat to be M into delta H of fission, that's the mass times the specific latent heat of fission, then plus MC delta T. So here we're going to substitute all these using the appropriate numbers here. So that will be, the mass here is actually 60 grams, which is 0.06 kg. So that will be 0.06 times 3.36 times 10 to the power of 5, then plus 0.06 times 4.2 times 10 to the power of 3, then times the change in temperature here will be 80 minus 0, which is 80. So guys, when we multiply this and then add these products together, we are going to have 40.32 kilojoule. And that's it for this question. Option C is the answer to this question. So let's go ahead and consider the next question, guys. So that's question number 5 here. It says, a solid of mass 0.5 kg initially at 50 degrees Celsius melts at 60 degrees Celsius. Calculate the quantity of heat required to melt it completely. So guys, over here we have the specific heat capacity of the solid to be 1.0 kilojoule per kilogram per Kelvin. Then the specific heat of fission to be 2.0 kilojoule per kilogram. Alright, so here guys, we actually noticed that there is a mix-up here. So the specific latent heat of fission of this mass is supposed to be 1, and then the specific heat capacity is now meant to be 2. So solving with this, we're going to have that the mass 0.5 kg times the specific latent heat of fission 1.0 kilojoule per Kelvin is going to still be 0.5 kg, and this plus the mass 0.5 kg times the specific heat capacity of the solid, which is 2 kilojoule per kilogram per Kelvin, then times the temperature change, that's 60 minus 50, that's 10. So this will here be 10. So when we have 0.5 plus 10, that's 10.5 kilojoules. So guys, since we have 10.5 kilojoules here, that means if we convert this to joule, we are going to have 10,500 joules, and that's option D here. Option D is the answer to this question. So let's go ahead and consider the next question, guys. Okay, yeah, that's question number 6 here. It says specific heat capacity 26.4 joule per kilogram per Kelvin of a body means that when 26.4 joules of heat energy is supplied to a body of A mass 1 kg, the temperature rises by 1000 Kelvin. B mass 1000 kg, the temperature rises by 1 Kelvin. C mass 1000 kg, the temperature rises by 1000 Kelvin. D mass 1 kg, the temperature rises by 1 Kelvin. So guys, the answer to this question will be option D. This actually signifies that when 26.4 joules of heat energy is supplied to a body of mass 1 kg, the temperature rises by 1 Kelvin. And that's it for this question. Option D is the answer to this question. So let's go ahead and consider the next question, guys. So guys, the next question here is question number 7. It says thermal energy added or removed from a substance that changes the state of the substance is called A. Heat of reaction, B. Specific heat, C. Latent heat, D. Calorimetry. So guys, the answer to this question is option C here, latent heat. So guys, the next question here, question number 8 here says a piece of copper of mass 20 grams at a temperature of 110 degrees Celsius was dropped into a mixture of ice and water at 0 degrees Celsius. If the final steady temperature of the mixture is 0 degrees Celsius, calculate the amount of ice that melted. So let's take specific heat capacity of copper to be 0.4 joule per gram per Kelvin, and then the specific latent heat of fusion of ice to be 330 joule per gram. So guys, in order for us to solve this, we are going to have that the heat lost by the copper is equal to the heat gained by the ice. So guys, if we have this like this, it means that MC delta theta for the copper will actually be equal to M into the latent heat of fusion of ice. So guys, if we use this, then we are going to have the mass, which is 20 grams of copper. Guys, since we have this in grams, that's 20 grams of the mass, and then the specific heat capacity is also in joule per gram per Kelvin. So we are not going to make any conversion here. We will just have 20 grams then times the 0.4 joule per gram per Kelvin, then this times the change in temperature, that's 110 degrees Celsius minus 0, which is 110. So guys, we're going to multiply these out, and then this should be equal to the mass times the latent heat of fusion of ice. So we don't know the mass of ice here, but we have the latent heat of fusion of ice here to be 330 joule per gram. So in that case, that would be M times 330. So that's 330 M. So if we have this and make M the subject of this equation, so M is going to be 20 times 0.4 times 110 over 330. So guys, when we calculate these out together, we're going to have 2.7 grams. And that's option B here, guys. So that's it for this question. Let's go ahead and consider the next question. So that's question number 9 here. It says the temperature of a piece of metal of mass 9 grams is raised from 10 degrees Celsius to 110 degrees Celsius when it absorbs 108 joules of heat energy. Determine its specific heat capacity. So, guys, we're going to solve this out together. So, since we know that the heat energy here is equal to MC delta theta or delta T, where M is the mass, C is the specific heat capacity, and delta theta or delta T is the change in temperature. So guys, the change in temperature here is from 10 degrees Celsius to 110 degrees Celsius. So that's 110 minus 10, and that's 100. So we also have the mass here, but the mass here is in grams. So since the specific heat capacity is in joule per kilogram per Kelvin, we're going to convert this mass to kilogram, and that's 0.009 kilogram. So recall that to convert from gram to kilogram, you just divide by 1000. So guys, since we have gotten the mass, we also have the change in temperature, and then we have the heat energy here. So we are looking for C here, that's the specific heat capacity. So to make the C the subject of this equation here, it will be that C is equal to the heat, which is 108 over the mass times the change in temperature. Mass is 0.009, and then change in temperature is 100. So in that case, we'll have 108 over 0.9. So 108 over 0.9 will give us 120. And that's option C here, guys. So that's it for this question. Let's go ahead and consider the next and last question, guys. So that's question number 10 here. It says, ice of mass 50 grams at 0 degrees Celsius was completely melted by 70% of the total heat energy supplied. Calculate the total heat energy supplied. So let's take specific latent heat of fission of ice to be 336 joule per gram. So guys, again, since we have the specific latent heat here in joule per gram, we are going to leave the mass in gram. We are not going to convert it. So we said here it was completely melted by 70% of the total heat energy supplied. So in that case, 70 over 100 times the heat here is going to be equal to the mass times the specific latent heat of fusion. So in that case, 70 over 100 times Q, where Q is the heat, is equal to the mass 50 grams times the 336 joule per gram specific latent heat. So guys, if we make Q here the subject of this equation, Q is going to be 50 times 336 times 100 all over 70. So guys, the answer to this question is going to be 24,000 joules, and that's option C here, guys. So option C is the answer to this question. So this is where we'll end this video for today, guys. If you enjoyed this lesson, please give it a thumbs up. Don't forget to subscribe to this channel if you're not yet a subscriber. Also, if you have any specific question regarding this video, you can drop your question on the comment section below, and we'll ensure to give you a response. Finally, guys, we want to encourage you to join our YouTube channel community. So you can join this channel community by hitting the join button below, and we'll see you right there. Thank you once again for watching this video, and see you on the next one.